Welcome back. So here we are going to design the state observers. So predictive state observer or full state observer, which is already discussed. Also discuss the pole placement technique, state regulator and its examples. So in these lectures we are going to design only the observers and also discuss the separation principles based observer design. So here current state observer and reduce observer. So as you know that there are different types of observers we classify based on the available measurements. One is the full state observer, second is the reduced state observer. Full state observer we already discussed in previous lectures. In these lectures we are just focus on the current state observer and reduced state observer, and also we are going to discuss the separation principle based observer design. So first we are going to discuss the current state observer. Why it is called a current? So in prediction observer, we are estimating the next label or next state variables value using the current value measurement. And so prediction observer arrives at the state estimation x cap k after receiving measurement up to yk minus 1. Then after that we can design the controller, that is the u minus k x. So x cap does not utilize the information on the current output byte. So in a prediction observer, so here we are, suppose current state we want to measure, so we have to apply yk minus one step before. Then we can get the a current input of the system for the controller. So this prediction observer, they are not going to utilize the y of k, means current output. They are taking the past value. So we have to use a memory device. We have to store these values. So these to avoid this problem, so we have to go for the current state observer. So for higher order systems controlled with a slow computer or any time sample rates are fast compared to computational time. So this delay between making a measurement and using it as control law may be placing. So here comes to the a computational time. So these computational time reflect in terms of the delays. So these delays affect the system. If these delays are larger compared to the sampling time, then these observer becomes as a any current observer becomes as a prediction observer. If these delays are less than the sampling time, then we can say that a current state observer becomes as a prediction observer. So there is no effect on the system output. So there is no computational delay we are consuming. So we are getting the same. So all prediction observer behaves like a current state observer. So there is no effect. So here computational delay should be less than the sampling time. A computational delay larger than sampling time, then we can differentiate between the prediction observer as a current state observer. So many systems computational time required, so they have given. So this is done by the separating principal process in two steps. So here they have given, so determine the x bar k plus 1. This is the approximation of the x k plus 1 based on the x cap and uk using the model of the plant. So we have to calculate x bar k plus 1. This is the nothing but this is the approximation of xk plus 1 based on the estimated value and input. Then we can calculate the next output, next level output, yk plus 1, to improve the x bar k plus 1. So this improved x bar k plus 1 is x tilde k plus 1. Sorry, xk cap plus 1. This is the next iteration. This x bar we can consider this the next step. So the observer based on this information is called a current observer. So we are using the current input and current output of the plant to estimate an next state value. So current observer we can write in this form equation 9a and 9b. So this is the x bar k plus 1 f, x k plus g uk, and x tilt is equal to x cap k plus 1 is equal to x bar k plus 1 plus m y k plus 1 minus c x bar k plus 1. So this is the current observer. In practice, current observer can be implemented exactly because it is impossible to sample, perform calculation and output with absolutely no time elapsed. So they are just considering this one. So we cannot able to implement this one if sampling time is smaller compared to the computational time or delay between the two blocks, observer and controller and plant process. These computational time is larger compared to the sampling time. Then we can differentiate between current state observer and predictive observers. So here, so we have to calculate the error dynamics. So this error dynamics we can get the using this error equations. So you know that this is errors in the state, this is the actual states, and this is the estimated. We are putting in the equations, so we are getting the same equation. So this is the error dynamics. So we can apply the same process. So here characteristic equations in the error dynamics Zi minus F minus MC. Take the determinants and calculate. And here we have to find m value. So m value we can use based on the desired value. So here how we can get this value, you can see. So current state estimated error equation is obtained by the subtracting actual and estimated state given in this equation. So we are getting this form. So we can put all the values. You know that the xk plus 1, this is the value, and in place of x cap k plus 1 we can put this value. So we are, after the simplification, we are getting that this is the current state observer. So in current state observer and normal state observer, you can see both are the difference. So here f minus mc into f, and here f minus mc. So here we can replace the C as a CF, then we can get the current state observer. So here we can design the value of M, that is called a current state observer gain. So M can be designed. So here also we can apply the correct equations. So based on the correct equation we can design. So now come to the second observer, that is called a reduced order observer. So why we are go for the reduced order, which is already discussed. We are assuming the all the state of the plant is available for the measurement and available for the feedback set. So if any other two plants, suppose in a system have the 10 plants, only 8 plants are measurable, only 2 plants are unmeasurable. Why we are going for the to measure the all the 10 states? We want only 2 states to measure, so we have to go for the reduced order observer. So we are not going to estimate all 10 states variable. We want only that estimation of the 2 state variables. So these are the 2 state variables are unmeasurable. We cannot able to measure. So in this way, we can opt for the reduced order observer. So suppose a system have the n states. So x1, this is the standard form, x1 which is directly measured. So x1 state variables, this is the column vector, is measured using the direct measurement, and xe is representing the state which is need to the estimated. So xe is the standard form for the estimation. So whole the state equation is divided into the measured and unmeasured variable. So you can see this is the equation. So we have to divide this form. So this is the system matrix F. So this F is divided this form. This is the G is divided in this form based on the order. These are the matrix. So F11 is the measured system matrix, F1E and FE1 and FE. So these are the equation they have given. So Y K is equal to also divided into two forms. So this is the A feedback system which is available for the measurement and 0 for the XC. So this is form. In this way, 11A and 11B we have to partition the matrices according to their sizes. So now we have to write these portions. So these partition matrix we can write we are interested in the unmeasured state. So unmeasured state variables we are want to measure. So we can write xek plus 1 is equal to fee xek plus fe1 x1k plus GEUK. This GEUK is known and FE1 x1 is also known. So overall these two terms are known values. So only this one unknown. So second measure dynamics. So yk plus 1 minus f1 yk minus g1 uk is equal to f1 exek. This is the unknown and this side is the all or the equations are measurable. So in this case, equation 12 have you can see these two terms are unmeasurable and this equation 13 is telling that these two equations are. So from equation 12 and 13 we can see that x can be replaced as a xe, xe can be represented as a x, fe represented by f and f1e can be represented as a c. So just like we are comparing as a previous observer. So x is nothing but equivalent to the x, FEE represent as equivalent to f and F1 is equivalent to the c. So GUK is equivalent to the this value. This is the nothing but GUK if we are comparing to the standard form and this YEK is nothing but this is the YEK. So in this way we are putting the value. So finally we are getting in this form. So this is the reduced order observer. This is the FE1. This is the input plus M. This one measurement. So this is the reduced order observer came. So this is the input. This is the suppose this is the G dash UK. This one and this is the Y E dash K error. So we are calculating the subtracting from equation 15 and 12 and calculating the error dynamics. So error dynamics x is equal to actual state variables minus estimated value. So here we are getting FE minus F1E. So you can see the FE nothing but is a reduced order system matrix that is equivalent to this order system matrix. M is the reduced order observer gain. F1E is the output matrix. So here C equivalent to F1E. So we can calculate the correct equations. So we are just simplifying the correct equation to obtain the value of F. So then we have to select the desired value poles location and obtain the correct equation and compare these correct equation and to calculate the M. So in this way we can apply and this is also applicable for the duality principles. So here the compensator design we are just going to select discuss the regarding the separation principle. So here you can see this is the plant equation is given and this is the sensor. We are getting the output, then output and input is applied to the observer. So observer may be current observer, may be full order, may be reduced observer, it depends on you. Then estimated value is applied to the controller. So this is the all of the state regulators. So here the problem is the how we are going to select the poles or desired poles locations of the observer as well as controller. So in this way we are just considering this. So they are here considering these equations are given that for the predictive observer we can design any observers. So here only one problem is getting. So here we can use the separation principle. Separation principles are telling that we can select the observer and control means the controller poles equations and observer poles location arbitrarily. They are not dependent to each other, but we have to make as a difference between observer and controller. So because here you can see the observer output is given to the controller. So means observer response is much faster compared to the controller. So observer response we can design or we can select the observer location, observer poles location in such a way that these poles lies near about the origins and controller poles location should be away from the observers. So generally we are considering 3 to 5 times away from. So as we are moving away from the origins or imaginary axis, the response of the poles or dominant poles, it becomes slow. When it is approaches the origin or origin axis, it becomes fast. So observer response we have to make as a faster compared to the control. So we have to first design, select the observer near about the origin. Then after that we can choose the controller. So this is the principles of the separation. So we are describing here. So here you can see f minus gk minus mc. So they are designing same u equal to minus kx we are putting. So we are getting this form. So this is the a transfer functions of the overall. K is the gain of the controller, m is the observer gains. So here we are considering the same equation as a previous we are discussing, t is equal to 0.1 seconds per sampling, and this is the f matrix, this is the p matrix. So here we are going to design. So reduce order observer. So you have to partitionate this one. So you can see that this is the C matrix, this is the system matrix. We are getting the this T, and this is the 1. So here we are Z minus 1 minus MT equal to 0. So we have to find the correct equations. For this correct equation we are desired at Z equal to 0.5. We can equate and calculate the M value. So we can get the M value and put all the equations. We are getting the this correct observer's equations. This is the observer equation, this is the control law for the controller. So in this way we can design and we can select the observer and control law equations in this way. So we are separating. So this is the transfer function of the observer based controller. Thank you for this, for the listening. Thank you.